Well, good afternoon, everyone, and thank you very much for connecting to today's webinar. My name is Harry Giordano. I am an adjunct faculty member at the University of Nicosia and have been teaching at the Mechanical Engineering Department from this past semester. So the topic of today's webinar discussion, from concept to production, how a spacecraft is born, was chosen from elements of my own experience and areas of expertise in space applications. Through this webinar, I plan to present how the design, manufacturing, testing, and safe operation of spacecraft is based on fundamental engineering principles, with mechanical engineering as one of the key backbones. But before that, a few words about me. My work experience covers project management, satellite manufacturing, monitoring, spacecraft operations, as well as personnel management and university teaching. For 5 years, I was involved in space robotics and the assembly of the International Space Station, while at the Canadian Space Agency. So apart from kinematic and dynamic analysis, pre-mission planning, procedure development, and real-time support for specific assembly flights, I was the point of contact for effects on attitude and reverse thruster control from the ISS and or the space shuttle onto the Canadian-built robotic arm, which assembled the space station. You might have actually seen the robotic arm being installed on the space station at some point. That was the beginning of my robotics involvement on the assembly station, on the International Space Station, up until 11A, which was at the end of 2002. Following that, I got involved in satellite operations, space segment management, and overseeing the manufacturing, testing, launch, and in-orbit acceptance of a geostationary satellite. The picture here was taken from the launch of the satellite on an Ariane 5 rocket in 2017 from Kourou in South America. Now, before these, I received my doctorate degree in mechanical engineering from Queen's University in Kingston, Canada, on the automation and control of nonlinear dynamic system, a thesis that was based on kinematics, dynamics, vibration, robotics, and control principles. And through education and employment, I have several publications, some of which are available and some that are not, unfortunately. Now, getting back to the webinar and the main scope, the title was From Concept to Production, How a Spacecraft is Born. But one could very well ask, why is there so much interest in space? What does space itself have to offer us humans? Well, this goes back to our early history, our innate curiosity and hardwired drive for discovering. For example, what is after the next hill, past the next mountain, the next valley or desert? What's across the next body of water, whether a lake or sea or ocean? And this is in order to satisfy our need for adventure and, of course, exploit the resources. And while doing that, we have managed to push the scientific and technical limits, challenge our existing knowledge, learn from experience and, of course, our mistakes, create new industries, improve and optimize processes, educate and transfer our knowledge to our colleagues and friends and kids and so on, communicate and share all these experiences with the objective of improving standards, our living standards and the well-being. Now, one could ask, how did human manage to do so, to improve the standards of living and the well-being? First, creating tools necessary for hunting, for defense, or to cook, build, cut, and saw. And then build shelters to protect ourselves from weather, fire, animals, including other humans, unfortunately. Create communities. And then by travel, initially by conquering the land, from foot to horse-driven carriages, to steam engine trains, to internal combustion, and now electric vehicles, either on wheels or by using magnetic levitation. And then by conquering the waterways, from early boats for a few passengers to large cruise ships, the size of a small city, and learning again from mistakes and improving designs for comfort, efficiency, and safety. And then by conquering the air, from early design concepts and sketches by Leonardo da Vinci, for example, to the first propeller-driven plane by the Wright brothers, to two-level passenger jet-powered planes and to new concept blended wing planes, to electric planes now in production that can travel 300 kilometers in 1 hour, which is what the little film is showing on the bottom. This is a concept that is currently in development, and it will be in production by 2025. Now that we've covered ground, the waterways and air, the next obvious hurdle will be space or environment to investigate. So through advances in rockets, spacecraft, landers, reusable vehicles, reusable rockets, and an ever-increasing interest in space exploration and habitation is where we are at this point. Now, one could very well ask, how do these improve our standards of living and well-being? Well, there are many reasons, and I will start with telecommunications, which I will go into further detail later on. Now, the ability to transmit communication signals, whether radio, TV, telephony, internet, cloud data, etc., to users on complete continents or to travelers over the oceans and in the air is a key reason for the interest in space. Now, such communication is made possible by spacecraft orbiting the Earth, either from about 36,000 kilometers from the surface of our planet. This is known as the geostationary orbit, or by spacecraft that are much closer to its surface. And I will present both of these approaches or philosophies a little later on. And then we can have navigation satellites, providing geospatial positioning with exact location and time. We're all very much aware of how these GPS devices are used in our smartphones, for example. The United States has its own system, the Global Positioning System, or abbreviated as GPS, and its fleet of many satellites and in multiple orbits. The European Union has its own system, the Galileo, which is already operational. Russia has its own, the GLONASS system, and China, the BDS system. And there's other countries that are developing their own systems for the exact same application. Past that, we have hundreds of other satellites, Earth observation satellites, which are very close to the surface of our planet, that observe our planet's environment, monitor the weather, lightning, atmospheric convection currents, wind direction and intensity, and also identify and track fires, dust storms, and other events on our planet. That's improving our understanding of our planet's forces and protecting us from them. Now, to understanding our places in the cosmos with incredible pictures from such space telescopes that can clearly see distant galaxies, formation of stars, and galactic events such as supernovas from a front row observation position just outside of planet's atmosphere. And finally, to advances in medicine, manufacturing process, and agriculture. Now, for example, the ISS is a unique platform for all these experiments, whether it is to growing plants in space that could then be used and support human habitation of the Moon and Mars, or by advanced medicine production, such as formation of special crystals in zero gravity, or even testing advanced technologies like robotics and autonomous systems necessary for, again, going into interplanetary missions and habitation of other satellites, natural satellites such as the Moon, or other planets such as Mars. Now, going back to the first reason for the interest in space, that was telecommunications. And obviously the existence of two approaches to such, by placing satellites in either the geostationary orbit or the low Earth orbit. And I will present both during my webinar. Of course, starting with the geostationary, you can see what the geostationary satellite actually does. It is an artificial satellite, 36,000 kilometers from the surface of the Earth, that completes one complete revolution around the Earth in 24 hours. And what is the advantage of that? See, for example, this little red dot. That little red dot is a simulated spacecraft that rotates around the Earth, and it does one complete rotation in 24 hours, much like the Earth does around its own axis. By doing so, if we place a satellite at that location, it means that a satellite dish that is installed on your roof, for example, of your house, does not need to be driven to track a satellite, since the satellite itself appears to be motionless from the surface of the Earth. And that is the whole principle behind a geostationary satellite. Now, in terms of what it does, it can provide broadcast services. Like I said earlier, radio, TV, whether it's HD, 4K, 3D, makes no difference. Broadband services such as internet, mobile communications, VSAT services, very small aperture terminals, that's what VSAT stands for. And of course, aeronautical and marine communications for ships and planes and so on, and also support crisis and defense communications. That is the overall purpose or the reason for existence of geostationary communication satellites. Now, I have a small film. Since a picture is 1,000 words and a movie is 1,000 pictures, I will now show you a very brief movie that was produced by one of the leading European satellite manufacturers, Innate Space, which is based in Cannes in Toulouse in France. It really presents the capabilities of their geostationary satellites, the communication services they provide, and it shows explorative use of their broadband, broadcast, and dual mission spacecraft, and obviously capabilities in launch compatibility. Now, there's some of the services: TV, triple play, broadband services. I'll just let you watch the movie. Especially necessary when there's no ground infrastructure for communications. That is the reason of existence of satellites, which can beam from space, all these services. Explorative view, we'll go through some of the main key components in subsequent slides. And you can now see the satellite in its deployed configuration with the solar arrays and the antennas deployed. That will be the configuration in space, but in order to fit the satellite within the capsule or within the fairing of any of the launch vehicles, you will need to fold the solar arrays as well as the antennas. And this is what this film actually demonstrates. And then brings in the launch vehicle components. Compatible to a series of different launch vehicles from Falcon 9, Falcon Heavy, Proton, Atlas, Ariane 5, and so on, Soyuz. So from the number of different missions, then we have on the geostationary plane, the satellites that this particular manufacturer has produced and launched in space. So that was one of the satellite manufacturers. There's Airbus also in Europe, OHB, Space Systems, L'Oreal, Boeing, and Lockheed Martin in the US, and some other and other manufacturers in Asia as well. But bottom line, all the geostationary satellites are pretty much all made out of the same or equivalent components. And you might have seen in this movie the brief exploded view of your typical satellite. And these are shown here, some of the main components, like facing the Earth, which the Earth is faced by this set of beams. A typical telecommunication satellite has a series of beams that transmit and receive communication signals for the the satellite's payload. To support this, a satellite uses specific beacons and horns, which are mounted on the satellite structure, onto which all other equipment are attached to. For example, the propulsion system, the main engine. You can see the main engine. This is used for the time that the satellite is, released from the launch vehicle, and all the way up until the satellite is finally moved to its final geostationary position. This main engine is used because it has the maximum thrust that the spacecraft can produce. And from that point on, we are using small thrusters that are located at pre-selected positions, obviously on the spacecraft, which will maintain its attitude or its pointing towards the Earth. We also have the solar rays that collect and harvest the electrical energy from the sun. We have the links that connect the solar rays to the body of the spacecraft, and what rotates the solar rays is the solar ray drive mechanism. The whole point of this mechanism is to maintain the solar rays facing the sun at perpendicularly to maximize the electric energy harvesting from the sun. It also charges the batteries, which are necessary for use while the spacecraft is in the Earth's shade 2 times a year for a period of 45 days, or when the moon casts a shade onto the sun, onto the spacecraft from the sun. Other communication module components are located at different panels within the spacecraft. We have the beams, like I said, panels, a star tracker to monitor the stars over the spacecraft, which is necessary to determine the attitude of the satellite. Antenna pointing mechanisms and deployment, which were used immediately after the satellite was released by the launch vehicle, and while it was moving towards its final geostationary position. Finally, we have avionics attached to the service module or the platform section of the satellite. And all the transmitters, receivers necessary for the communication payload are situated on or attached to a different segment, different part of the spacecraft. Now, if you can imagine, there's a lot of components, as you saw earlier. Now, putting all these components together in their own specific operations groups, one can see that the main subsystems that form a satellite are propulsion, electrical power system, thermal, attitude, communication, the structure, data handling, and mechanisms. Now, each of these is composed by a number of units. For example, a typical propulsion system is composed by chemical and or electric thrusters. The main engine, like I said earlier, was used from launch until the final placement in the geo position. Valves, tubing, pressure regulators, propellant tanks, and of course, all these are hardware connected to software that all gets fed into the onboard software for management and control. Like every subsystem is composed by a number of units, and each unit is composed by a number of subunits. And each subunit is composed by a number of components, much like what this diagram actually shows. Like if we look at the control moment gyro, for example, this is not a space equipment, this is a kit but it follows the same logic. Like a component would be this little connector, this bracket, and nuts and bolts, and it would be wires that connect to different modules within each of the subunit. An accumulation of all these different components, we can see in the dashed yellow line, generate a small subunit, or one of the 4 CMGs. And then when you put all these 4 units onto the housing and do whatever else needs to be attached to it, that defines a new unit. This particular unit is a CMG, or the gyro. The gyro is part of the attitude control subsystem. It's one of the key subsystems of any typical spacecraft. So once we put together all these subsystems, we have now generated or produced a spacecraft that is ready to be launched to space and operate for a number of years as per its intended lifetime in orbit. Now, once all these components are machined or 3D printed or manufactured as defined in the manufacturer's plan, they are assembled either manually or robotically. The final set of tests are at the system level, as this new movie, again provided by Thales Alenia Space, presents. So we can see a number of different components, subcomponents, units. And here is the almost completed final system. Let me just back up a little bit. When I say almost completed, is because the solar arrays are on it, but the antennas are not. And this is simply a restriction of the particular vacuum chamber, which is not large enough for the complete antennas in their assembly to be included within the actual vacuum chamber. The vacuum chamber itself is another testing facility. You have liquid nitrogen on the exterior, on the interior of the vacuum chamber. And the spacecraft is exposed to the environment that it will see in space, from minus 120 Celsius all the way up to 60, 70 Celsius from inside this satellite's body. And that is done by heaters that are attached, are added on top of the spacecraft, shown right here. And by that, you can thermally cycle the spacecraft during the 4 or 5 weeks of testing. Thus making sure that all the components are working properly. There's a proper communication, and there's every unit, especially the payload as well as the platform unit, perform well within the specifications and requirements. Now, once the spacecraft is tested in the vacuum chamber, we can complete its assembly with the actual antennas that have already been tested in vacuum separately. And here we have the antenna, a typical antenna that is mounted onto the spacecraft, but held by helium balloons simply to negate the effects of gravity. This motor and all these links are designed to operate in space. In space, we have zero gravity, so we don't have to worry about the weight of the system. We just simply have to worry about the mass, the inertia of it, which is a different dynamic, has a different dynamic effect on the spacecraft. Now, if we did not include the helium balloons, the mechanisms will probably collapse under the weight of the complete system. That's why we are offsetting the weight of the antenna and the links and all the motors that are attached to the spacecraft by including these balloons, which are tuned and provide the necessary lift depending on which antenna and what its weight is. Now, you can also notice a number of different bumps and valleys and contours on this reflector. You can maybe see them better now. The reason is this is a custom-made antenna, which in a way shapes the coverage on ground by introducing these valleys on the antenna itself. The objective of that is to have a pre-desired coverage zone at specific power levels, and the only way you can do it is by doing all these forms. And there's a lot of engineering behind the antennas and the preparation of the graphite base that this the carbon fiber sheets are attached to or laid on in order to generate a predefined, a pre-desired shape. Sorry, I need to go back to I pressed inadvertently. I should go to this point. Okay. Number of different tests to complete the whole round of tests, including vibrations testing, acoustic chamber testing, and here's the anechoic chamber where the payload is tested. And once everything is certified and tested and well within the specifications, the spacecraft is ready for launch. It is shipped by air to Cape Canaveral. It depends on which launcher is used, but the one that we launched from was in Kourou in French Guyana. Now, as I mentioned earlier, the antennas are typically manufactured to meet specific ground coverage and power demands. Now, take this satellite as an example. It has 6 beams. This is the Eutelsat 9B satellite. 6 beams. There we go. 1, 2, 3, 4, and 5 and 6 on the top Earth deck, and implying that we have 6 different coverage zones. Now, the coverage of each is shown here they're primarily for European use. And you can see that the shaping that we've talked about earlier, we can change the values and the contours on the antenna just to have a predefined shape, which is can be realized in the 5th antenna right here when it covers from England, France, Germany, all the way into Greece, Turkey, and Syria, and the northern Egypt. In order to have that peculiar shape and not a perfect circle or an oval shape, you need to have introduced those valleys and contours onto the antenna. And you can very, very quickly see that not the whole of the Earth is not completely covered by the satellite. Mind you, that was the as per design of the particular satellite. But if we want to have complete coverage of the Earth with satellites, then we might need to think of different options. And another option of the geostationary arc will be to introduce additional high-power satellites. But each of these satellites is very, very time-consuming to manufacture, very expensive. And there's some other drawbacks, which I'm going to go through a little later on in the presentation, and are essentially covered by a different approach. This is the approach.
Since the beginning,
use the low
World
Earth
Wide Web
option
has never
or
been
low
worldwide.
Earth. So let me just
But in
pause for a second.
2021, a new and
Increase the volume.
truly global 5G-ready network will fix that. Say you're working on the edge of the world and need to do a video call. Perhaps you're mid-ocean or mid-air. Wherever you are, you'll have a signal. OneWeb will connect your device through a customized terminal that can be as small as a briefcase and just as compact. Whatever your location, the terminal encrypts your data and sends it at high speed to our satellite fleet passing overhead. These spacecraft are radically innovative, built in our own factory at 1/50th the traditional time and cost, shrunk to the size of a washing machine, yet engineered to deliver powerful throughput. Month by month, we're growing our satellite fleet, and by 2021, we'll have not only the global spectrum rights, but the network reach to deliver truly worldwide coverage. And here's the revolutionary part. The fleet will be in low Earth orbit, 30 times closer to Earth than geostationary satellites. This gives you a stable, real-time connection with no interruption or annoying lag. What's more, our fleet always keeps moving, orbiting in a constellation design that creates seamless coverage. Each satellite uses a set of beams to cover an area the size of Alaska. Terrain is no obstacle. From its flight path and pattern, our fleet can always find your signal, so we can get you online from even the trickiest locations, with look angles that geo-satellite broadband simply can't deliver. We maintain high-grade system resilience from 2 ops centers using state-of-the-art ops concepts. Cloud architecture gives us powerful scalability and control remotely. For example, we can remove satellites at the end of their service life, so that the only trace we'll leave in space is on your screen right now. Now back to that video call of yours. We beam your data back down to Earth to our nearest satellite network portal. Then via one of our point of presence gateways, positioned in secure locations trusted by global providers, it re-enters the web. The journey you've just watched takes, at most, 1/10 of a second. And there they are. Your video call is good to start, whether with colleagues or your family back home. So from 2021, you need never be out of signal or out of mind. OneWeb will connect you from unconnectable locations and keep you productive on the move. It'll be a breakthrough year when OneWeb technology creates real human progress, connecting everywhere, for everyone.
Okay, that was a nice little film from OneWeb. Thank you very much to all the people that are working and trying to save the company. It is an incredible project with over 600, 700 satellites planned for placement in orbit. It will be about 1,200 kilometers from the surface of the Earth, and as you can see, it has a completely different philosophy from geo telecommunication satellites. And the key advantage here is that it will have global coverage, irrespective of whether you are on the Arctic Circle, Antarctica, and behind big mountains. There's no real shading effect because the satellites are not simply located on the equator, which is the plane where all the geostationary satellites are located. The fact that they go around the Earth means that every single person on the planet, provided they have this the ground infrastructure, which is very, very cheap, and as I will show shortly, will be able to receive internet at very, very low latency, very brief delay, incredibly low delay, which is not the case for geosatellites. But again, they have different market, views. Now, this low Earth communication satellite is not the only one. OneWeb is one of the companies. Starlink by Elon Musk is another one. They also have plans. They already launched a number of spacecraft in orbit, and I think the overall plan is to launch anywhere up to I think 12,000 spacecraft. And the astronomers will not be very, very happy because all these individual satellites will obviously interfere with stargazing from the surface of the Earth. But again, that is one of the design considerations. These new satellites will have a sunblock or something to divert sunlight from the sun towards the and reflect that away from the Earth. That way, they will appear as dark spots on the sky, and they will not obstruct astronomers' viewing of the skies. Now, the low Earth orbit communication satellites will have global coverage. Because there's so many of them, and continuously changing their role as they move into their respective orbits. They will have they will guarantee stable connection, very, very low latency because of the very small distance away from our planet, and thus we'll be able to provide high-speed internet. Now, every single dot that you see on this diagram is a location for a specific spacecraft, and following a certain path, and all these paths will be crisscrossing about the two poles at different altitudes. So all this is automated. Their trajectories are pre-planned. The coverage zones are shown here, and they will cover the entire planet. The minimum ground infrastructure is another major advantage of having low Earth satellites, because it only needs a small briefcase of a satellite dish that you can put on the house or side of your tent, and provide the very little amount of power to operate this ground infrastructure in order to have continuous internet anywhere on the planet. The satellites, there's far smaller, but cheaper to manufacture, and obviously faster. I think the plan is to have 2 per day. And another advantage is that you can stack as many as 34 satellites within any launcher. And there's a picture that shows ones that were launched recently from, again, French Guiana. The first 2 are deployed at the same time, and then groups of 4 are released at the same time to negate all the any attitude changes on this structure. Now, you can imagine that deploying that many satellites in miscellaneous orbits, because we're looking at maybe close to 800 OneWeb satellites, 12,000, if not 42,000. I've heard 2 numbers. I'm not quite sure which is the actual case for Starlink fleet. But we're looking at thousands upon thousands of satellites, all sharing the same orbit or different altitudes. And it's a recipe for disaster if you don't take good care of the path, and if you don't make sure that all the satellites are operating properly. And a result of such a collision would be really catastrophic. You may have seen the Hollywood movie Gravity. And so in order to minimize such an eventuality and safeguard a clean space, OneWeb is looking into methods of collecting and assisting a safe and planned re-entry of a phased satellite. One is shown in this final film. But of course, this is not the only option. I'm just going to let you watch. It's got a small magnetic grapple device, a small grapple device, which can be captured by different ways, either magnetically or by an actual mechanical grappling device, or by other means. And if this satellite was not going in the right orbit, then you simply just track it down and go and collect it, and then push it back into the Earth's atmosphere for a controlled re-entry and destruction. That way, you will not have this satellite going off track, potentially ruining other satellites, creating a cloud of space debris with the exponential propagation of space debris generation. And at the end of the day, when you have such a chain reaction event, you will essentially make the low Earth orbit completely unusable for future use, because it's so filled up with essentially garbage that you cannot really operate any of the valuable satellites, such as the observation satellites and so on and so forth. So there's a lot of different solutions for collecting debris and making sure that everything is working properly in order to secure clean space. It is simply a matter of engineering design and the use of fundamental principles of mechanical, electrical, and computer engineering in a never-ending process of optimization and improvement. Now, as you already know, this University of Nicosia offers the following engineering degrees: electrical, computer engineering, civil environmental engineering, oil and gas and mechanical engineering. From the slides so far, we have seen that what it is that makes a spacecraft, from its millions of components to subunits, to units, to subsystems, and to the final product itself, a fully operational satellite with its built-in redundancies and high reliability for safe operations in space. And we can appreciate that all of these components are built on engineering principles. Like, for example, if we look at propulsion, its units operate on the mechanical engineering principles of heat transfer, fluid flow, dynamics, stress, strain, on welding practices, and then X-ray and ultrasound techniques to assure safe operations within the required pressure specifications, and on strict vibration suppression control in order to survive both the launch and the space environment for its planned years of operation. So therefore, even in these high-profile space applications, the engineering principles are the same. Now, for the propulsion subsystem, one would need the knowledge from both mechanical engineering and electrical engineering. Now, if we add links from the remaining subsystems to the engineering principles available at the School of Sciences and Engineering at the University of Nicosia, one can easily conclude that mechanical engineering, then electrical engineering, and then computer engineering would generate the required skill set for these engineering students for such fields, but not limited to, obviously, and will be able to progress from a design concept to the manufacturing and production of any system, from satellite to a coffee machine to a computer to anything that needs to be produced either in mass or in individual units. So in summary, whether to meet immediate needs or simply satisfy their curiosity, humans have always looked for ways to improve their standards of living, well-being, and satisfy their innate drive for adventure and exploration. Now, transitioning from these needs to conceptualizing designs and solutions in order to manufacture efficient, safe, and reliable products has been a long process over many, many centuries that required a mix of trial and error, educated guesses, developing analytical approach methods and optimizations, tool generation, and more recently, computer-aided design, analysis, modeling, simulation, manufacturing, and testing processes. Understanding and controlling mechanical system behavior requires a methodical approach that builds on fundamentals and progresses from the understanding of statics, kinematics, system dynamics and vibrations, to manufacturing, robotics, and control systems. All of these being integral components of mechanical engineering and taught at the University of Nicosia, Department of Mechanical Engineering. Thank you very much for your attention. This concludes my presentation on the on concept to production, how a spacecraft is born, and I'll be more than happy to answer any of the questions that you may have. Okay, thank you very much, everyone. Have a good rest of the day. If you have any questions, you can get in touch with me via the university. Thank you.